Find the area of the region bounded by the given curves. Y equals root x, y equals x squared, and x equals to 2. So let's begin by plotting y equals root x. We should know the graph of root x appears something like this. The next function would be y equals x squared, which we know is the parabolic curve. So that would be y equals x squared. And then the last thing we need to plot is x equals to 2. Before we can plot that, we have to figure out what the corresponding x value here is. In order to do that, we need to make these two functions equal to each other. So x squared must be equal to root x. If we get rid of the square root, by squaring both sides, x to the 4 is equal to x to the 4 minus x is equal to 0, x cubed minus 1 is equal to 0. So either x is equal to 0 or x cubed minus 1 is equal to 0, which means x cubed is equal to 1. If we take the third root of 1, it's equal to 1. So we know this point of interception must be 0. This must be x equals to 1. Therefore, the line x equals to 2 is drawn to the right of that. Now, this isn't to scale, but that's not so important. What's more important is to make sure the line was drawn to the right of this point of intersection. So this is x equals to 2. The region that is bounded between all three of these curves would be this region here. So in order to integrate this, we can see that we have a boundary on the bottom, which happens to be this curve. We have a boundary on the top, which happens to be this curve. So we can use the basic formula of top curve minus bottom curve, starting at 1 and going to 2. So our starting x value is 1. We're going to integrate until 2. The top curve was x squared minus the bottom curve, which was root x. And we need to integrate this with respect to dx. So at this point, this should become a trivial question. The antiderivative of this is 1/3 x cubed minus, remember root x is the same thing as x to the half. So we need to add 1 to the exponent, which is going to be 3 over 2. We can divide by 3 over 2, which ends up being a multiplication of the reciprocal, 2 over 3. And we need to evaluate from 1 to 2. So we begin by plugging 2 in. This is going to become 1 over 3, 2 cubed, minus 2 over 3, 2 to the power of 3 over 2, minus, we're going to substitute in 1, which is going to become 1/3, and 1 cubed is a 1, minus 2 over 3 times 1 to the power of 3 over 2, which also happens to be a 1. So this is going to be 2 to the 3, which is 8 over 3, minus, this here is 2 times 2 to the 3 over 2. Using exponent rules, this becomes 2 to the 5 over 2, divided by 3, minus 1 over 3 minus 2 over 3 is negative 1 over 3. So this is going to become plus 1 over 3. 8 over 3 plus 1 over 3 becomes 9 over 3, which is 3, minus this term here. So this is our answer for the area. Let R be the region in the first quadrant bounded by the following curves. Calculate the following volumes. So question A is the volume obtained by rotating the region about the x-axis. Question B is about the y-axis. Let's begin by first plotting the curve. So y equals x cubed, we know should be a graph that looks approximately something like this, and there's nothing to draw down here because we're only interested in the first quadrant. 2x minus x squared should be a quadratic that looks like this. We can accurately plot this by first finding the x-intercepts. So the x-intercepts, if we go ahead and set this equal to 0, if we factor this, we get x, 2 minus x. So either x is equal to 0 or x is equal to 2. So we know we have one intercept here, and we're going to have another intercept here, and then we're going to have a quadratic that goes through this. Now, you can draw it any which way you want, but you want to try to figure out where this point of intersection is in order for this graph to be accurate. So we know these are the intercepts, but we're not exactly sure where the peak is relative to this point of intersection. So we know this is a 0, and we know this is a 2. The peak has to occur at the middle. It has to equal to 1. This peak has to occur there. So let's go find where this point of intersection is between the two curves. In order to do that, we make the equations equal to each other. So x cubed equals 2x minus x squared. Bring everything to one side and factor. We get x we can factor out. So x squared plus x minus 2 is equal to 0. X plus 2, x minus 1 is equal to 0. So either x equals to 0, x equals to negative 2, or from here, x equals to positive 1. The only one that makes sense for this point of intersection is to be x equals to 1. So that means this point here and the peak intercept. So we're just going to draw this a little bit more accurately. So there we go. The peak and the intercept occur there. So this is as accurate as we're going to get. This is the region that's enclosed by the curves. So that is what we are going to be rotating. So I'm just going to erase this to zoom this in a little bit more. So we have our cubic, we have our quadratic, we know this value was 0, we know this value was 1. We don't care about the 2 that was here because that's not part of the region we are rotating. We only care about this region here. Because x is equal to 1, we know this curve here was y equals to x cubed. This curve here was y equals to 2x minus x squared. Plugging 1 into either one of these equations tells us the corresponding y value here is also equal to 1. So we have hopefully everything we need in order to set up our integrals and solve for parts A and B. So they haven't mentioned which method you can use, so you can use cylindrical shells or washers. It's possible one method may not work. In this case, we're going to go ahead and use washer method because that seems just pretty easy based on what we have here. So we are rotating about the x-axis for part A. So we're going to have two radius. One radius is from here to here, and the other radius is to this curve. When we set up our integral, it's going to be from our smallest x value to our largest x value, which is 0 to 1. Then it's going to be pi of the big radius squared. So this big radius is equivalent to whatever the y value of this curve is, and y is equivalent to 2x minus x squared. So it's going to be 2x minus x squared squared minus pi of whatever the smaller radius is. This smaller radius is equivalent to the y value, which is equivalent to x cubed. So it's going to be x cubed squared. And again, the reason for squaring this is because it's supposed to be pi big radius squared minus pi small radius squared. So if you want a representative washer, it would look something like this. The actual shape is probably going to be like a flower petal shape kind of thing down there. And we're integrating this with respect to x. So let's go ahead and solve this. If you want, you can try the cylindrical shell methods. It may or may not work. I'm guessing it's probably not going to work because you have too many x's here. You wouldn't be able to isolate for x. So this method, what we can do is factor out the pi to make our life easier. So then you have 2x minus x squared, which we need to expand. So if we expand it, if we square this term, we're going to have 4x squared. Then 2 times this term times negative x squared, which is already taken into account because of this negative here, plus this term squared, which would become x to the 4, minus x cubed to the power of 2, which is really just x to the 6. So all we're doing this is expanding this as much as possible. Then we have 0 to 1, 4x squared. If we expand this, minus 4x cubed, plus x to the 4, minus x to the 6, dx. So this integral we can go ahead and solve now. The antiderivative of 4x squared would be 4x cubed over 3. For this one, the 4 would remain. It would become x to the 4 over 4, so the 4's are going to cancel out, plus x to the 5 over 5, minus x to the 6, actually x to the 7 over 7, and we need to evaluate from 0 to 1. Don't forget the pi, that's in front of everything. So if we plug in a 1, this is just going to be 4 over 3. This is just going to be minus 1, because 1 to the 4 is just a 1. This is going to become 1 over 5. This is going to be 1 to the 7, which is a 1, divided by 7. Minus, we plug in zeros. Everywhere we have an x, if we plug it in a 0, everything is just going to evaluate to 0. So we just got to go ahead and simplify this. And to save a bit of time, I've plugged it into the calculator. This here simplifies to 41 over 105, and we still have the pi, so that answer remains. This is the volume for part A. So just again, if you wanted to, you could try cylindrical shells here, but I believe you will not be able to do cylindrical shells for this question because you won't be able to isolate for x. So let's redo this for part B now. I'm going to go ahead and copy the graph for us. So this graph, we now have to go ahead and rotate about the y-axis, which would be this axis here. So what that means is we're going to rotate each of these points. So let's say you took this and you had a representative thing, you'd be rotating it this way. But that's if you want to use the washer method. And if you wanted to do that, you could, but again, you're not going to be able to isolate for x, so we can't go ahead and use that method. So instead of the washer method, let's use the cylindrical shell method for this question. For the cylindrical shell method, you need a height for whatever your cylinder is, and then the radius of that cylinder. So again, this is height, and this is radius. Because we are rotating about a vertical axis, our cylindrical shells will be with respect to x. So x means we're going to go from 0 to 1, and it's going to be 2 pi, whatever the radius is, times whatever the height is. So let's go ahead and fill those numbers in. The radius is going to be whatever the x value of this curve is at that point in time, so that's going to be x. And height is going to be whatever this y value is minus this y value. So the upper y value is equal to 2x minus x squared. The lower y value is equal to x cubed, so minus x cubed dx. So a height is all of this. And now this integral, we can go ahead and expand before we solve. So the 2 pi will pull out as a constant. We have a 0 and a 1. We multiply the x in, so we get 2x squared minus x cubed minus x to the 4 dx. The 2 pi is going to remain. Antiderivative of this will be 2x cubed over 3 minus x to the 4 over 4 minus x to the 5 over 5, evaluated from 0 to 1. If we plug in a 1, all the x's basically go to 1, so it's not going to affect us in any significant way. So it's going to be 2 over 3 minus 1 over 4 minus 1 over 5 minus, if we plug in a 0 everywhere, all those x's will go to 0. So all that remains is to simplify this fraction. And if we simplify this, we're going to end up with 13 divided by 60, which we've got to multiply by the 2 pi, so it's going to be 26 pi over 60, or if we go ahead and reduce 13 pi over 30, that's the volume of that region here if it was rotated about the vertical y-axis. Evaluate the following indefinite integral. Looking at this function, we realize it's a rational function, so we should go ahead and attempt to find partial fractions. So we're going to go ahead and rewrite the numerator, x squared plus 8x minus 3. The denominator can be factored into x squared, x plus 3. So in the denominator, x by itself is linear, but it repeats twice. So we have a over x plus b over x squared. Plus, we have another linear factor, x plus 3, so it's going to be c over x plus 3. We're going to multiply all of this to the right, so we're going to be left with x squared plus 8x minus 3 equals, so if we take this entire term and multiply it to the right, at some point we're going to have to multiply that term in. So a over x times this term would be ax, x plus 3. Then b over x squared times this term would be b, x plus 3, because the x squares would cancel out. This times this term would simply be c x squared, because x plus 3 would cancel out. In order to quickly figure out the coefficients, we can use a bit of a shortcut. We can let x equal to 0. So if we let x equal to 0, on the left side we have negative 3. If I plug a 0 into this x, it's all going to 0 out. If I plug 0 into here, we'd be left with 3b. Plug a 0 into here, it would 0 out. So we would have negative 3 equals to 3b. Therefore, b is equal to negative 1. So at the moment, we know b is equal to negative 1. Now let's go plug in a different x value. So another x value we can plug in is negative 3. Now, the way we came up with x equals to 0 is we just looked at our terms here and we asked ourselves, what x value can we plug in to zero out any of these factors? So if I plug in x equals 0, it would have zeroed this and this out. Another x value I can plug in is -3 because that will zero out this and this factor. So on this side, if I plug in -3, -3 squared would be 9, plus 8 times -3, which would be -4, minus 3. We know it's going to zero out this factor and this factor, so we're going to be left with c times 9, because -3 squared is 9. If we go ahead and simplify this, we end up with -18 equals to 9c, so therefore -2 is what c is equal to. So now we know what b is and we know what c is. There's no other value of x we can plug in that will zero out any of these factors, so we can just choose another random number, let's say 1. If we plug in 1, this would become 1 plus 8, which is 9, minus 3, which is 6. If we plug in a 1 here, we would have a 1 times 1 plus 3, which is 4, plus b times 1 plus 3, which would become b times 4, plus c times 1 squared, which is just c. However, we know 4a is going to remain, but 4b, because we know b is equal to -1, this is going to become -4. And c is equal to -2, so this is going to be -2. This becomes 6 equals 4a minus 6, 12 equals to 4a, 3 is equal to a. So this is one way we quickly figured out that a is equal to 3, b is equal to -1, and c is equal to -2. So what this means is we can go ahead and integrate this term instead. So this integral is equivalent to the integral of a over x with a equal to 3, plus b over x squared. B was equal to -1, so instead of plus, it's just -1 over x squared, plus c, which we know is -2, so it's actually going to be -2 over x plus 3. And we're going to integrate these partial fractions instead of what we had originally. The integral of 3 over x would simply be 3 ln absolute value of x. -1 over x squared is the same thing as -x to the -2. So the negative remains, x to the -2 would become x to the -1 divided by -1, minus 2 here is a constant, and then this part here, 1 over x plus 2, is ln absolute value of x plus 2 plus c. So overall, our answer is 3 ln absolute value of x plus x to the -1, which is the same thing as 1 over x. The negatives are going to cancel out. Minus 2 ln x plus 2 plus c, that is our overall answer. Now, if you don't know the formula for this one, you would use a u substitution with u equal to x plus 2. Question number 3. Evaluate the following indefinite integral. So looking at this integral, it looks like we would be able to apply trig substitution, but the problem is it's not x squared minus some number squared. So what we're going to do here is complete the square. In order to complete the square, we're going to add 4 and subtract 4. By doing so, when we take the first 3 terms here, we can rewrite that as x minus 2 squared, and then we still have the minus 4. So now this is something squared minus 4. We can do a simple u substitution in order to convert this into an integral where we can use trig substitution. So our u in this case would be equal to x minus 2, which means dx is equal to du. Substituting that in, we get 1 over root u squared minus 4, and now we can apply trig substitution to this. For trig substitution, because it's something squared minus a number, that means we can use the substitution a secant theta. A in this case, because a squared is 4, a would be 2, so our substitution will be u equals 2 secant theta. The derivative, therefore, is 2 secant theta tan theta, and we stick on a d theta here as well. So substituting in our denominator where there was a u, it became 2 secant theta, so when you square it, it's 4 secant squared theta. And this dx here, or sorry, it shouldn't have been a dx, it should have been a du once we convert it over. This du gets turned into 2 secant theta tan theta d theta. And now we go ahead and simplify. First, if we factor out a 4 and then take it outside the square root, it becomes a 2. leaving us secant squared theta minus 1. And then using this identity, secant squared theta minus 1 is technically tan squared theta. The square root of tan squared theta is just tan theta. So now a few things cancel out. The 2 and the 2 cancel out, tan theta and tan theta cancel out, leaving us secant theta d theta. This is considered one of the basic integrals, so you should know what the formula is. If you don't know what the formula is, you would have to use valuable time trying to derive this solution. So the antiderivative of secant theta d theta is ln absolute value secant theta plus tan theta. Now the original substitution was u equals 2 secant theta, and that was the original trig substitution. Based on that, we can recreate this right angle triangle. So u is technically 2 secant theta, so u is equal to 2 times 1 over cosine theta, which is what secant theta is equal to. Cosine theta is 2 over u. So if this here is theta, this is adjacent over hypotenuse, which is how we know 2 is here and u is here. Therefore, by Pythagoras, this must be u squared minus 4 root. Using this triangle, we can go ahead and substitute. Secant theta, technically, secant theta is 1 over cos theta. So cos theta would be 2 over u. Therefore, secant theta is the inverse, u over 2, which is how we got this. Tan theta is opposite over adjacent, which is how you get root u squared minus 4 over 2, which is how we come up with this. So we undid the trig substitution, but then we also have to undo the u substitution. So everywhere you have a u, now you replace it with an x. So this is your final answer. Determine whether each integral is divergent or convergent. Looking at this integral, we have an infinity on the boundary, so this is an improper integral. The very first thing we have to do is rewrite it as a limit with a letter approaching infinity. Let's go ahead and make it limit as b approaches infinity. Therefore, the integral becomes 1 to b ln x divided by x to the 4 dx. Now what we need to do is go ahead and figure out the general antiderivative or the general integral, and we can do it to the side here. We're going to go ahead and use integration by parts. Our u is going to be ln x, and our dv is going to be x to the negative 4, because we can bring this into the numerator, and that would make the exponent negative. We can't really use substitution here, it wouldn't work out, so that's why we're going with integration by parts. So for integration by parts, we need a du, so the derivative of ln x is 1 over x. The antiderivative of x to the negative 4 is x to the negative 3 over negative 3, which we could rewrite as negative 1 over 3x cubed by bringing this negative exponent to the denominator and the negative sign up front or up to the top. Then according to integration by parts, it's going to be u times v, which is how we get these terms. Determine whether each integral is divergent or convergent. Looking at this integral, we have an infinity on the boundary, so this determine whether the integral is divergent or convergent. So looking at this integral here, we have boundaries of 0 and 2 over 3. We have a denominator here. Question number 3.
So there was this one, there was that integral one, and then there's this one. Okay.
So we know this function will be discontinuous whenever the denominator is equal to 0. So that means when 2 is equal to 3x or x is equal to 2 over 3. It turns out that this boundary here is equal to 2 over 3, so the function is going to be discontinuous there, so this is an improper integral. So we need to rewrite this as a limit. The limit will be as b approaches 2 over 3 from the left side. Since we're going from 0 and we're approaching 2 over 3, that's why it's from the left side. So from 0 to b of that integral. Now the antiderivative of this function is simply going to be negative 1 over 3 ln absolute value of 2 minus 3x. This is a formula you should know, but if you don't, then the only other technique you can apply is u substitution with u equal to 2 minus 3x, and you will still get the same antiderivative. In this antiderivative, we need to evaluate from 0 to b. So first we plug in b, which is this portion here, minus, we go ahead and plug in 0. So we'll deal with this after. If we plug in 0, 3 times 0 is going to cancel out, So we're just going to be left with the absolute value of 2. And negative will force us to be positive 1 over 3. Now, we have to go ahead and plug in 2 over 3 from the left side. So if we plug in 2 over 3 here, we know this term in here is going to go to 0, but when we do that subtraction, we're going to be left with a 0 that's slightly positive. So this is a bit of a typo here. This should actually be 0 that is slightly positive. Again, the reason being it's going to be 2 minus a number that's slightly smaller than 2/3 times the 3. So 3 times 2 over 3, and it's a little bit smaller. Overall, this is going to be very close to 0, but it will be slightly positive because this number here overall will be slightly smaller than 2. So overall, this is going to be a 0 to the right. And if we take the absolute value of 0 to the right, it's just a 0 from the right. There's nothing we need to do here. Absolute value of 2 is also just positive 2. Taking a look at our logarithmic function, ln x is generally like this. So ln just to the right of 0, we can see the function is going to negative infinity. So this becomes negative 1/3 times negative. Determine whether the integral is divergent or convergent. So find the solution to the following initial value problem. Looking at this equation, it appears we can separate this. First, we take this term and bring it over to the right, which will make it negative. Then we need to isolate the x terms and the y terms. The dx that's in the denominator here, we're going to multiply over to the right. And at the same time, this y minus 1, we're going to divide to the left. This x squared plus 1, we're going to also divide to the right. So we're just separating the variables. Again, dx is multiplied to the right. X squared plus 1 is divided to the right. Y minus 1 is divided to the left. Once we have this in this form, we've separated the variables so we can integrate both sides of the equation. Integrating this side, this is a formula you should know, it simply becomes ln absolute value of y minus 1. If you're not sure of the formula, then you can do a u substitution with u equals to y minus 1 in order to solve this integral. This integral here, again, this one is one you should know, but if it's something that's harder to remember, we can do a simple u substitution with u equal to x squared plus 1. Therefore, du dx is equal to 2x. Solving for dx by multiplying it over to the right and dividing by 2x onto the left, if we were to substitute it in, this would become negative 3x, which remains. The denominator becomes u, and dx becomes du over 2x. At this point, the x's cancel out, leaving us a constant of negative 3 over 2, which you could pull out in front if you prefer, and 1 over u du. The antiderivative, or the integral of 1 over u, is ln absolute value of u, and we need to put our plus c now. And remember, u was equal to x squared plus 1, so we have to substitute that back in. Now, we do have an initial condition. Y of 0 is equal to 2, so this is a good point to go ahead and plug that in. So what this means is that your x value is equal to 0, and your y value is equal to 2. So we can go ahead and substitute that in. This y becomes a 2, this x becomes a 0, and then we can simplify. This becomes 2 minus 1, which is 1. Ln of 1 is simply equal to 0. This becomes 0 squared plus 1, which is 1. Again, ln of 1 is 0, so this whole term goes to 0. Therefore, c must be equal to 0. Going back to this original equation, which is copied down here, we had a plus c, but we know now c is equal to 0, so it disappears. So now we just have to go ahead and solve for y. We get rid of the ln by putting everything to e on both sides. The e and the ln will cancel out here. E, and this will all go into the exponent of e. Then what we can do is, there's a minus 1 here, so we can bring that over so it becomes plus 1. So technically this is our answer, but we can simplify this further. This number here, because it's in front of a ln, we can make it an exponent of x squared plus 1 using logarithmic rules. So it becomes e to the ln of x squared plus 1 to the power of negative 3 over 2. And the reason for doing that is the e and the ln cancel out, giving us a slightly more simplified answer. So while this is correct, this is more simplified here. This is your final answer for this initial value problem. A curve C is defined as the parametric curve x equals t plus 1 and y equals t squared minus 2. Part A, sketch the curve. There are two ways we can do this. We could create a table of values, but the easier way is to eliminate the parameter. Using the x equals t plus 1 equation, if we solve for t, we can see t is equal to x minus 1, which we can then go ahead and substitute into the second equation. So instead of t squared minus 2, because we know t is equal to x minus 1, we get x minus 1 squared minus 2. We should recognize this is a quadratic equation that has been shifted to the right by 1 and down by 2, and it opens upwards because it's a positive x. So it's a quadratic equation. 1, negative 2 is where the bottom lies. We can also quickly figure out the y-intercept by making x equal 0. When x equals to 0, we would see that y is equal to negative 1. So that's it for part A. For part B, set up the integral to calculate the arc length of the curve from 0 to 2. So in general, the arc length formula is this formula here written in green. It's our starting parameter to our ending parameter, square root of dx dt squared plus dy dt squared. So going back to our equation here, if x is equal to t plus 1, the derivative of this with respect to t is equal to 1. So dx dt is equal to 1, and the derivative of y with respect to t is equal to 2t. So when we plug into our formula here, it's going to be 1 squared, because we still have the squared here, plus 2t squared. And if you want, you could simplify this. 1 squared is 1. 2t squared would become 4t squared. And again, the parameter goes from 0 to 2. So those are our boundaries. And we integrate with respect to t. This is the arc length they've asked us not to evaluate, so this is all we require for part B. Part C, show that the curve has a horizontal tangent line at the point 1, negative 2. So that means, first, we know that whenever we have a horizontal tangent line, the slope must be equal to 0. The slope in general is dy dx, but whenever it's parametric, it's dy dt divided by dx dt. We need a horizontal tangent, so we need this equation to equal to 0. The only way it's going to equal to 0 is if the numerator is equal to 0. So again, a horizontal tangent when dy dx is equal to 0, but because dy dx is equal to this equation, we only need the numerator to equal to 0 in order to find where we have a horizontal tangent. We know from earlier the derivative with respect to t was 2t. If we set it equal to 0 and solve, we get t equals to 0. So therefore, as long as the parameter is equal to 0, we know dy dt is equal to 0, which means 0 divided by anything is equal to 0, so dy dx is also equal to 0. All we have to do now, that we know what t is equal to 0, plug t equals 0 in to find the x value and the y value. X in general is t plus 1, y in general is t squared minus 2. If I plug in 0, I get an x value of 1. If I plug in 0 here, I get a y value of negative 2. So therefore, the point where we have a horizontal tangent is 1, negative 2, and that's exactly what they asked us to show. So that takes care of part C. Find the formula for the area of the surface generated by rotating the polar curve r equals f of theta, and you're rotating from theta some value a to b, which is located between 0 to pi. The rotation is about the polar axis. So the polar axis is essentially the x-axis here. Because we're going to be using polar coordinates is a form of a parametric equation. Let's start with the parametric equation for rotating a curve about the x-axis, since essentially that's what this happens to be. So for the parametric equation, it would be 2 pi y, the derivative of x with respect to the parameter squared, plus the derivative of y with respect to the parameter squared, square root of that, and the whole integral is with respect to the parameter. We know the parameter here is theta. They're saying r is a function of theta. So now, what we're going to do is we're going to replace everything in here in order to come up with an equation. And we want to replace this and convert everything to be in terms of theta and r. In general, for a polar coordinate or polar equation, x is equal to r cos theta. Y is equal to r sine theta. We know we're going to need the derivatives, so if we differentiate this and use the product rule, that means r, which we know is a function of theta, and cosine theta. In order to use the product rule, what we're going to end up with is r prime cos theta minus sine theta times r using product rule. And another way it could be written is this. Similarly here, if we use product rule, the derivative of r is r prime times sine theta plus the derivative of sine theta, which is cos theta, times r. So we come up with the derivatives using product rule. And we know y at some point will be replaced with r sine theta. This is dx d theta squared. So what we can do is before we plug it in, let's go ahead and square this term and simplify. But also, let's go ahead and find dy d theta squared and simplify. So dx d theta squared, think of this as a plus b squared. It's the first term squared, the second term squared, minus 2 of the first and the second term squared. So all we did is write out the expansion of this term. Similarly for dy d theta, because it's a plus, it's the first term squared, the second term squared, plus 2 times each of this, which is how we come up with this term. Now, under the square root, we're going to end up adding these two terms. So if we go ahead and add these two terms, this plus this plus this plus this plus this plus this, notice the middle two terms are the same terms, but opposite signs. So they are going to cancel out. So these two terms here will go ahead and cancel out. So therefore, we'll only be left with this first term, this term, this term, and this term, which is how we got to this line here if we were to add those two terms together. Now we can expand this sum by simplifying using exponent rules. If we bring the square in, it's the derivative squared cos squared theta. Because I see another derivative here, let's just write it beside there. So this exponent, when we bring it in, it would be the derivative squared sine squared. Going back to this one, r squared sine squared theta. And finally the last one, r squared cos squared theta. And the reason we did this is because now if we factor out the derivative, you're left with cos squared theta plus sine squared theta. If we factor out the r squared, you're left with sine squared theta plus cos squared theta. And we know these terms go to 1. So essentially, they disappear, leaving us dr d theta squared plus r squared. So all of this tells us this is equivalent to that. So we're going to substitute that in here, and we know y is r sine theta. So all you do is you plug this in and you have your answer. So it's going to be from a to b, 2 pi y, which is r sine theta, and the square root of the term we just developed, d theta. This is how you find the surface area for the scenario that was described for any general curve that we're going to rotate about the polar axis. Use the formula in part A to find the surface area generated by rotating the polar curve about the polar axis, and do not evaluate the integral. So they've told us that we have 0 to pi over 4 here, and there's an arrow missing, but it was pointing to this point of intersection here. So if this is theta equals to 0, this point of intersection here is theta equals to pi over 4. So when we create our integral, we can go from 0 to that point of intersection, which is pi over 4. That means you're going to take this top half of the curve here, and you're going to rotate it 360 degrees. And when you do that, you're going to form a balloon-looking shape. Now, this balloon-looking shape on this side would also be rotated, but the surface area of this would be equal to the surface area of this. So once we find the surface area of this, all we have to do is multiply by 2 in order to get the surface area of the entire shape. So this is the formula we developed on the previous page for part A. We know we can go ahead and solve for r. At some point, we will solve for r and substitute that in for r here. We also need to go figure out the derivative. So in order to find the derivative, we're going to use implicit differentiation because it's r squared. The derivative of r squared is 2r, but then we're taking the derivative of r with respect to theta. On the right side, using chain rule, the derivative is negative 2 sine 2 theta. So if we simplify, dr d theta in general is negative sine 2 theta divided by r. Now we need the derivative squared, so we can figure that out before we plug it in. So everything we just found here, we're going to square it, and then we're going to multiply the exponent in, expand the exponent in. The negative 1 will disappear. This becomes sine squared 2 theta, and r becomes r squared. However, we know what r squared is equal to. R squared is equal to cos 2 theta. So we got to replace this r squared with cos 2 theta. So now we know the derivative, we know r squared, and r you can solve for by simply taking the square root. It would be just root cosine 2 theta. So this was my r, we made it root cos 2 theta. This is my derivative squared, we've replaced it. And r squared is the original equation, cos 2 theta. Notice here, everything is in terms of theta now. So this is our integral. We have to multiply by 2. Again, going back to the fact that we have to find the surface area of this side when it's rotated as well. So using symmetry, we only multiply by 2. Our parameter will go from 0 to pi over 4, because that takes care of this first quadrant rotating. That's all we have to do for this question. We do not need to evaluate or simplify further. Test the following series for convergence or divergence. Taking a look at this series, it looks like the integral test would be pretty good because we can do a substitution in here in order to solve. In order to do the integral test, first we have to decide what our function would be. So our function is basically the same terms we have here, but we're going to replace the n's with x's. So it'd be x squared e to the negative x cubed. Now in order to do the integral test, you have to check your 3 conditions. F of x must be always positive, which is the case here. Every term would always be positive. It must also be continuous, and again, f of x will be continuous. There is no domain restrictions here, so there's no discontinuities we need to worry about. And thirdly, we need to make sure it's a decreasing function. There's a couple of ways to show it's decreasing. One of the easier ways is to take the derivative. So if we take the derivative using product rule, this is going to be our simplified version of the derivative. Notice we have 2x and we have 3x to the 4. This x to the 4 term is going to be overall bigger, and because there's a negative sign in front, you're going to have a small number minus a bigger number, which means overall you'll have a negative number, which means your derivative is always negative. Therefore, we've shown that we are always decreasing. So the next step, after we check the 3 conditions, is to take the improper integral from the starting boundary to the ending boundary. So 1 to infinity of this function. So because it's an improper integral, we have to replace that infinity with a letter. So let's replace it with the letter b and take the limit as b approaches infinity. Now we need to solve this integral first before we deal with the boundaries and the limits. When we've solved it on the side to the right here, it's going to be a u substitution with negative x cubed. Once you work your way through the u substitution, you're going to end up with negative 1 over 3 e to the negative x cubed as your overall integral, which is why we are using that here. Now we plug in our boundaries b and 1, so that's the next step here. If we plug in infinity, infinity cubed is infinity, but there's a negative in front, so it becomes negative infinity. E at negative infinity is 0, so this entire term goes to 0. And here we would have a negative and negative, which is positive. 1/3, negative 1 cubed would still be negative 1. The negative is outside of the cubing. So this here would simplify to 1 over 3e if we don't want the negative exponent. Because this improper integral exists, because it converges, by the integral test, since the integral converges, the series converges as well. Test the following series for convergence or divergence. So taking a look at this series, we see a sign in the numerator. The trig function sign, the maximum value it could have is a 1. So this function here must be less than or equal to 1 over 1 plus 2 to the n. The numerator would never be bigger than a 1. So we have this inequality here, and we can think of something we want to compare against by looking at this function. We have 1 over 2 to the n. So we can use a comparison test if we got rid of the 1 down here. So for the comparison test, we can create the new series Bn. This is a geometric series with r equals to 1 over 2. Therefore, Bn is convergent. And because this here was my An, and this is Bn, we know if this is smaller than this, and this is smaller than that, An must be smaller than Bn. So since An is smaller than Bn, and because this one is convergent, Therefore, our original series converges as well. Test if the following series converges or diverges. Here we have a negative 1 to the power of j. This indicates it's an alternating series, so let's attempt the alternating series test. Our bj term would be just everything other than the negative 1 term, so it would be root j divided by j plus 5. The alternating series test requires two things. First, make sure it's decreasing. So bj plus 1 must be less than bj. We can see clearly here the numerator will get bigger faster than the denominator, which is why it is a decreasing function. But if you prefer, you can take the derivative to show it's negative, and that will also show that it's a decreasing function. The second condition is take the limit at infinity and make sure the limit is equal to 0. You could use L'Hopital's rule, but here the degree of the numerator is 1 over 2. The degree of the denominator is a 1. Because the numerator is smaller than the denominator, we know the limit will equal to 0. So we've satisfied both conditions. Therefore, by the alternating series test, our original series must be convergent. Find the Taylor series for e to the 2x centered at a equals to 3. Also, find the radius of convergence. So the Taylor series, assuming we're centered at 3, would be f of 3 plus the first derivative at 3 times x minus 3 over 1 factorial, second derivative at 3 times x minus 3 squared over 2 factorial, and this pattern would continue on forever. So what we'll do is first find the first few derivatives and functions evaluated at 3. So our function is e to the 2x. If we plug in a 3, f of 3 is equal to e to the 6, since it'd be 2 times 3, which is 6. In order to find the derivative, we would use chain rule. That would give us 2 times e to the 2x. The derivative, if we plug in 3, would be 2e to the 6. Find the second derivative. Again, we would use chain rule and multiply by the constant of 2, giving us 4e to the 2x. Plug in 3, we get 4e to the 6, and you can see the pattern, what's happening. We're going 1, 2, 4, 8, e to the 6. So that is up to the third derivative, and because we see a pattern forming, we don't really need to continue forward. We know this series will continue on forever. What we need to do now instead, though, is replace f of 3 with e to the 6, since that's what it was equal to. Replace this f prime 3 with 2e to the 6, x minus 3, 1 factorial. Replace f double prime with 4e to the 6, x minus 3 squared 2 factorial, and so on. This pattern continues on forever. Now, technically here, we have an x minus 3 to the power of 0 and a 0 factorial, but that's not typically shown. But the reason I'm mentioning this is it makes sense to start at an index of 0 and work our way to infinity because this goes on forever. So notice there's a couple of different things that we need to figure out in order to find the formula. The denominator is going to be n factorial. Remember, this is 0, 1, 2, and 3. We're starting at 0, so your denominator is simply going to be n factorial. The exponent here matches your n value as well. Exponent is 3 when n is equal to 3. This is equal to 2, 1, and here we don't see the term because the exponent was 0. So x minus 3 to the n remains. E to the 6 is just a constant everywhere, so the e to the 6 won't disappear. But we have one other term. We have a 2, 4, 8, which means we technically have an invisible 1 here as well. The only thing that works for this, because it goes up by a multiple of 2 each time, is 2 to the n. When your first value is 0, 2 to the 0 is 1. When your n value is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So this here is the power series formula. This is the power series expansion. And 0 times anything is 0. So this is saying it does not matter what the value of x is, our limit will always be less than 1. Therefore, the radius of convergence is infinity because it doesn't matter what number we're going to be plugging in, there's an infinite number of options. Evaluate the integral of 1 over 1 plus x to the 7 dx as a power series. Also find the associated radius of convergence. We're allowed to make use of the fact that 1 over 1 minus x is equivalent to x to the power of n as an infinite power series, and the radius of convergence of that is also equal to 1. So what we can do is forget about the integral for now. Let's just start with the function 1 over 1 plus x to the 7. If we can rewrite it as a minus sign in the denominator, so 1 over 1 minus negative x to the 7, whatever this term is what we can replace this term by. In our case, we have negative x to the 7, so we can replace that x with negative x to the 7. So this is our power series. We can simplify. We have a negative 1 technically, so it's negative 1 to the n, and x to the 7n using exponent rules. That is what this function is equal to in terms of a power series. However, we want to integrate that, so we integrate this side, which means we integrate this power series. Again, we are starting at n equals 0 and going to infinity. Okay, when we integrate, we know we're going to have a constant, so we're going to write that constant down right away. Negative 1 to the n, we are integrating with respect to x. So if you want, make sure not to forget to write down the dx term here. Because we are integrating with respect to dx, what that means is anything that does not have an x is a constant. Negative 1 to the n is a constant, so it remains. X to the power 7n. Well, like any other x to the n, we would use the power rule in order to integrate. It would have been x to the n plus 1 divided by n plus 1, but in this case, my original exponent was 7n. So it's x to the 7n plus 1 divided by 7n plus 1. So that means this integral here can be expressed by this power series. Now, we know this original series has a radius of convergence of 1, meaning x must be less than 1. So using that fact, instead of x less than 1, for us, our term that we plugged in was negative x to the 7. So negative x to the 7, the absolute value must be less than 1. If we take the absolute value, we're just left with x to the 7. And if we take the 7th root of both sides, absolute value of x must be less than 1. Therefore, the radius of convergence is still 1, because that number did not change. Find the